I went to a power engineering expo expecting to see new products. Limits of voltage, limits of regulation, limits of phase balance, limits of temperature. And in many cases, the difference between a system that works and one that doesn't came down to surprisingly practical details. So in this video, I want to show you what actually stood out to me, not as a trade show visitor, but from the perspective of how electrical systems really work. This was Ampere in Brno, a European trade fair focused on electrical engineering, power systems, automation, components, measurement, and energy infrastructure. But instead of treating this as a general expo tour, I want to use it as a way to look at something more useful. How electricity is actually transformed, distributed, managed, cooled, protected, and measured in the real world. This won't be a complete overview of everything that was there. It's more like a map of the topics that I think matter the most. One of the first things that immediately stands out at an event like this is the scale of power equipment. A transformer is one of those devices that almost everybody knows exists, but most people never really look at closely. Here you can see several medium voltage to low voltage distribution transformers from different manufacturers with different ratings, different voltage combinations, and even different vector groups. Some of them were rated at 400 kV amps, others 630 or 800 kV amps. Some had labels like DIN 1, DIN 5 or DIN 11. Some showed combinations such as 22 to 0.4 kV, while others used values like 12 to 1.1 kV or 38.5 to 1.1 kV. And this is exactly where trade show footage becomes more interesting than just visual b-roll. Even a simple nameplate tells you that a transformer is not one universal object. It is always designed for a specific system, a specific voltage level, a specific grounding philosophy, and a specific application. You can also immediately see another real-world theme that comes back later in this video: heat. These ripped walls are not decorative. They are part of how the transformer gets rid of losses. So even here, at the level of basic distribution hardware, thermal design already matters. And once you start noticing these details, the next question becomes obvious. Where do these transformers actually sit in the larger system? The clearest bridge between theory and reality was the substation equipment. This is where the abstract idea of the power grid turns into something physical. Incoming medium voltage, transformation, protection, switching, and low voltage distribution.
Protože na nízkém napětí jsou vysoké ztráty, tak vlastně dálková distribuční síť je na vysokém a velmi vysokém napětí a do místa určení, tam, kde se odebírá elektřina u malých spotřebitelů nebo větších, tak je potřeba to vysoké napětí transformovat na nízké napětí a k tomu právě slouží trafostanice.
That is one of the most important ideas in the entire electrical system. Electricity is not distributed at low voltage over long distances because the losses would be too high. So the grid uses higher voltage levels for transport, and then substations step that voltage down closer to where power is actually needed. And what I liked here is that this wasn't just a theoretical explanation. You would actually look inside a compact concrete substation and see the chain, transformer, low voltage switchgear, and insulated medium voltage equipment. There is also compact medium voltage units with functions like circuit breaking, load switching, and earthing. In other words, not just boxes, but carefully engineering switching points in the network. On the low voltage side, the picture becomes even more practical. Bus bars, PAN connections, surge protection, breakers, meter sections, auxiliary power, ventilation, communication modules, and the messy but essential parts that make a system actually operable. If you are used to North American residential systems, some of these European distribution and cabinet layouts may look quite different. The modularity, dinner rail ecosystem, three-phase distribution style, and the way neutral and protective conductors are handled are all worth a closer look on their own. So already at this point, one thing becomes clear. Power distribution is not just about moving electricity, it is about doing it with acceptable losses, proper protection, and infrastructure that matches the real network. But properly, the most interesting topic for me was battery storage. Not because batteries are new, but because they are often misunderstood. People tend to think of them as simple energy containers. What came through in the interviews much more strongly was something else. Batteries are really tools for managing energy, power peaks, and system behavior.
K čemu se to používá? Primární použití této baterie nebo tohle z toho chytrého řešení je vlastně poměrně širokospektrální a dá se použít třeba pro stříhání špiček, pro ukládání energie, pro obchodování na spotu. Záleží, co si klient přesně definuje a co vlastně klient od toho očekává.
That already makes the role of a large battery system much more specific. It is not just there to store electricity. It can absorb excess energy, help during demand peaks, and in some cases even improve the economics of the whole installation. One practical way to think about it as an energy buffer. When the system has surplus energy, the battery can absorb it. When the load spikes, the battery can help cover that peak. And that can matter not only technically, but economically. For example, by reducing how demanding the installation is on the grid connection. Another thing I found useful was the discussion about limits. Not marketing advantages, limits. There are legislative limits, certification limits, grid code requirements, and then there are hardware limits. How much capacity is actually usable, how the thermal system is designed, how noisy the system is, and where it can realistically be installed. Velký limit je velikost nebo hluk. Jak jste na tom vy?
Ano, to je taky pravda. Víc hlučný na tom jsou v podstatě ty ventilátory, které můžete vidět v maketě, nebo na téhle maketě za sebou. A co se týče obecné hlučnosti, když si to pustíme v manuálním režimu, když ty ventilátory testujeme, tak hlučnost je pod nějakých 50 decibelů.
That was especially interesting because this particular system combined liquid and air cooling, not just for heat removal, but for keeping the battery cells in a narrow and uniform temperature range.
Chladicí jednotku, takzvaný LTMS systém, který funguje na principu tepelného čerpadla, vzduch-voda, který vlastně případně bere nebo dodává teplo, záleží, která část se hřeje nebo chladí víc. A pak jsou zde odtahový ventilátory, který přebytečný teplo vlastně vytahují ven z té baterie. Každý z principů má nějaké svoje výhody i svoje zápory a vlastně tady tohle s tou dvojkombinací, co právě před sebou vidíme, dochází právě k optimálnímu udržování teploty, protože pro life-počlánky je velice kritický a zásadní, aby vlastně udržovali konstantní teplotu.
And then there was another very practical point. More battery is not automatically better. If a system is oversized relative to how the building actually behaves, the return on investment gets worse. So again, the real question is not how much capacity can I buy, but how well does this capacity match the way the site really uses energy? I also filmed other battery systems at the expo, and while I didn't get equally deep explanations there, they reinforced the same impression. Behind the outer cabinet, these are layered systems with power electronics, battery modules, communication, switching, and thermal management all tightly linked together. So the big takeaway here is that battery storage is not a magical solution. It is a control tool, a buffer, and whether it makes sense depends on regulation, operating profile, thermal design, and economics. Closely connected to battery storage is another topic that often gets simplified too much: inverters. Because saying that an inverter turns DC into AC is true, but not nearly enough.
Tentokrát za námi se nachází průmyslový měnič. Tenhle měnič vlastně se používá k přeměnění stejnosměrného proudu na střídavý. To znamená, že tu energii, co jde z panelu, vlastně převádí na tu energii, co máme doma v zásuvkách nebo prostě mezi fázema.
Můžete nám zase říct nějaké limity těchto střídačů?
Pokud bychom se bavili o té legislativní věci, jako je soulad s PPDS, tak všechny tyhle střídače, všechny tyhle řady 30, 40, 50 mají certifikát prohlášení o shodě s PPDS, to znamená splňují aktuálně legislativní požadavek. Co se týče jejich hardwareových limitů, tak tyhle střídače se především liší od předchozí verze nebo i od konkurence nižším startovacím napětím, to znamená, ty střídače nastartují už od 180 V a hlavní jejich výhodou jsou vyšší zkratové proudy na MPPT. To znamená, že vůči předchozí verzi tam došlo prostě k navýšením, protože i vlastně jak se vyvíjí obecně výroba těch fotovoltaických panelů, těch modulů, tak vlastně výrobce už dávají větší zkratové proudy a samozřejmě, když ten střídač s tím neumí pracovat a došlo by k nějakému v vozovkách zkratu, tak může dojít i k poškození toho střídače. A dimenzování, štění, kabeláže, všecko v návaznosti na doporučení výrobce.
What matters in practice is not just that conversion happens. What matters is how the inverter behaves in the real network. Předpokládám, že zase výstup je asymetrický a třífázový.
Ano, tohle to už je dobrá otázka, děkuji za ní. Ne. Tyhle střídače už jsou symetrické, protože jsou to síťáky a vlastně tam se potom řeší regulace pomocí dispečerského řízení, který je vlastně povinností v rámci legislativy. Když máte elektrárnu na 30 kW píků, tak zde je výstup čistá symetrie, to znamená, že když příklad vyrábí 20 kW, těch 20 kW podělí mezi 3 fáze a tím musí odpovědět na tu druhou otázku, je to třífázový výstup.
That is a good example of something that sounds small, but actually changes the whole application. Industrial grid-tied inverters are often expected to behave symmetrically across phases.
To, co vidíte za mnou, tak je vlastně rezidenční řešení, kde máme střídač, který opět už je zase asymetrický, protože české domácnosti hodně trpěly právě tím, že třeba v zahraničí funguje součtové měření a zde v Čechách máme fázové měření, to znamená měření po fázích. Tenhle ten míč umí 100% asymetrii.
This was one of the strongest insight at the entire expo. In some systems, what matters is not just how much power you have in total, but how that power is distributed phase by phase. And once you start thinking in those terms, batteries and inverters stop looking like isolating products. They become parts of a coordinated system shaped by grid rules, metering logic, backup requirements, and the behavior of real loads.
Další důležitou zmínkou je tento optimalizér s novým označením MERC 600 VPA0 a ten je především důležitý pro takzvaný rapid shutdown a fire safety. To znamená pro bezpečné odepnutí v případě poruchy nebo požáru, aby vlastně hasiči, když by museli stoupit na střechu, tak aby ty stringy nebo to stringování bylo při odepnutí na bezpečné napěťové hladině, aby je to s prominutím nepokopalo.
Even smaller components around the inverter matter. For example, optimizers used for rapid shutdown can be important for safety and emergency access, especially in rooftop photovoltaic systems. The expo also showed a broad range of other power conversion hardware, dinner rail power supplies, UPS modules, balancing modules, redundant modules, frequency drives, and even high compact high voltage DC supply solutions. That wider context is useful because it reminds you that power electronics is not just one thing. It is an entire ecosystem of conversion, backup, control, and distribution hardware. So the lesson here is simple. Electricity is not just generated and consumed. It has to be converted in a way that matches the grid, the load, and the protection philosophy of the installation. One of the themes that kept coming back in multiple conversations was cooling. And I think this is one of the easiest things to underestimate when looking at electrical systems from the outside. Whether we are talking about transformers, power electronics, batteries, processors, or custom industrial hardware, heat is always there in the background. And once the temperature window becomes critical, cooling stops being an accessory and becomes a design constraint. What I repeatedly heard was that good cooling is not just about adding fins or a fan at the end. The base has to be thick enough to spread heat properly. The size and shape of the fins matter. Airflow matters. And in many applications, the thermal solution has to be designed around a required temperature range for the actual components. This also ties directly back to the battery systems from earlier. Once you want stable performance, long life, and predictable behavior, Thermal management becomes part of the systems, not an afterthought. In other words, many electrical limits are not purely electrical, they are thermal. Finally, there is the category that is easy to overlook at any expo, the small things. Terminal blocks, surge protective devices, fuse holders, combiner boxes, connectors, ferrules, stripping tools, cable handling tools, the things that are really the headline, but very often decide whether an installation is clean, safe, and serviceable. What stood out to me here was how modular and system-oriented many of these solutions were, especially in the DIN-rail world. You could see that a lot of practical engineering happens at the level of interfaces, where conductors enter, how they are terminated, how protection is arranged, how maintenance is made easier, and how mistakes are prevented. And of course, none of this matters such if you can't measure what's happening. The expo also included power quality instruments, oscilloscopes, spectrum analyzers, and other diagnostic tools. A reminder that understanding electrical systems is not only about building them, but also about verifying and troubleshooting them. So what did I actually learn at this expo? I learned that modern electrical systems are much less about isolating products than they are about interactions, voltage levels, losses, phase behavior, cooling, protection, communication, and measurement. And I think this is the real value of seeing this equipment in one place. Not just to look at what exists, but to understand how all these layers fit together. In the next videos, I want to go deeper into the most interesting parts, a special distribution infrastructure, battery systems, inverter behavior, and the hidden thermal component level details that make these systems work.